Okay. Unit 3 progress check 7, 8, and 9. I'm going to go through this very briefly. I'll go through some more detailed, more difficult problems, but for the most part, I'm going to be going through this quickly so you can not spend 15 minutes listening to me ramble on. All right. Part 7a is we give you a table of values. They give you g of x equals f of the quantity x squared minus x, and ask for the derivative. I need to use the chain rule. That's all. So it's f prime of x squared minus x times 2x minus 1, and we evaluate that, and then we go. So don't overthink it. Part B is definitely more involved. That's why I gave this little pages thing. This is the solution. Okay, comes up to -5, and I will go over the answer right now. So there's two aspects of this that are a little bit tricky. First and foremost, they want f prime, a double prime of 0. So what that means, what we're supposed to do, and maybe we don't know this, is we're supposed to take the second derivative of g. We have the derivative of g. I gave you pink and blue here. We want the second derivative needing the product rule and the chain rule. So the second derivative of f prime of x squared is f double prime of x squared minus x times the quantity 2x minus 1, so on and so forth. I'm going to leave this to you to look at, okay? We got the pink and the blue being the first and second term, and once we get it to this point, we evaluate it at 0. This becomes -1, and all of these things clean up right here. All of this cleans up very nicely to here. A little bit of algebra here, and we get to -5. Okay, so I'm not going to explain this to you. Just know you start off with the product rule right here. You have to use the chain rule as well. And then you evaluate at 0, and you get your final answer. Part C is there a value where we can guarantee that g of c between 0 and 3 will give us 5? Well, that means the intermediate value theorem. So we need to determine that it is continuous. Because it's twice differentiable, it is continuous. We need to mention that. We then evaluate g at 0. Well, g of 0 is f of 0. So we just plug in the number of 0 and get that. We know that to be 4. We do the same thing for 3. G of 3 is equal to f of 6, which is equal to 7. So then we know that g of 0 is 4, g of 3 is 7. Therefore, by the intermediate value theorem, there must be some c that gives us 5. We must cross over that. We can show a little graph here. We can do whatever we want to do. But we must mention continuity, we must mention the intermediate value theorem, and we must explain the process. Okay? The next piece is so we want the average rate of change of f equaling to the instantaneous rate of change of h. So we find the average rate of change of f by our table of values. So we look for f of -3, which is -5, so on and so forth, and we find our average rate of change using our table of values to be 3. We then plug this into our calculator, and we set it equal to 3. We get a graph like this. If we wanted to solve it individually, algebraically by hand, we would divide by 4, take the ln of both sides and do cosine inverse, but because we have our calculators available to us, we need to know that we just do that. All right, it comes up to -1.8 something. Okay, number 8, the implicit differentiation. They give us a function and they say show that this derivative is equal to this. We just need to do implicit differentiation correctly. It's not that involved. We have the chain rule here with the implicit differentiation there. -24x becomes -24. We move this stuff around and we end up with y prime equals 4 over quantity 2y plus 1 quantity squared, which is our dy dx. We're happy. Okay? Part B is write the equation of the line tangent to the curve at the point -1, -2. Well, just like every other time we've done this, equation of the line means I need my slope and I need my coordinate point. Well, I'm given a coordinate point, and to find my slope, I simply evaluate my original derivative function at the coordinate point -1, -2. But -2, there's no x value, therefore we only evaluate it at -2. And when we plug it in, we end up with, we get 4/9, and there's my equation. Okay? Part C. Okay, part C is they want the second derivative. So I'm going to take my original function, my original derivative, and I'm going to find the second derivative. Okay, the second derivative, and we're going to use the quotient rule. So we do the derivative of the first, which is 0, times normal second, minus the derivative of the second. We need to use the chain rule here using implicit 2y plus 1 times 2y prime times normal first, all over the second squared. This is the second derivative. Now we just need to evaluate it at -1 comma -2. There are still no x values, so for every y value I plug in a -2, boom, this one is simplest -3. And for every y prime, I've already solved this, as they often do, this is going to be 4/9. So I replace that with 4/9. Then I do my basic algebra. Do not, at this stage of the game, allow for your algebra to cause errors. So we clean this up a little bit with a little bit of magic algebra, and we end up with 64 over 243. Okay, so part 8D is a little bit tricky, but not too bad. So 0.16 comma 0 is on the curve. Find the value of the inverse of y prime at 0. So what we need to know, we need to recall. Okay, so again, the 0.16 comma 0 is on the curve. Find the value of the inverse of this function, the prime at 0. So when we do these types of problems, it's really important for us to sort of identify everything we know before we dive into the problem. It doesn't help to be doing a problem and then discover what we know. So they gave us that this is on the curve. Therefore, this point, 0.16, is on the inverse of the curve. All right, so when we 16 comma 0, and then therefore that's on the inverse. Also, if we're looking for this function, it's important to know that the derivative at 1/6 is equal to, remember this is my input value, 4 over 2 times 0 plus 1 squared, or 4 over 1 or 4. So it's important to know these two things. Number one, I can switch my coordinate point. Number two, the derivative at 1/6 is equal to 4. And when I go down to my definition, this is what they're asking us. This is our question. So at this point, this becomes 1 over y prime of the inverse at 0. So this we can get from the chain rule, or this can be our rule that we have written down. But this is the inverse derivative rule. Therefore, this becomes 1 over. Remember, we determined that this inverse of 0 is 1/6, so this becomes 1 over y prime of 1/6, or 1/4. All right, again, getting this information together beforehand makes this a lot easier. Okay, so now we want to talk about number 9. In number 9, we're talking about two things. I don't know if you're looking at the AP Classroom or if you're looking at the document I sent you, but the document I sent you did not have these x values, so I'm just putting them in here, okay? So number 9 is, let g be the function defined by this, right? And I want to find the derivative at -1. So my derivative is going to be the quotient rule. So the derivative of the first, normal second, minus derivative of the second times normal first, all over the second squared. I then evaluated at -1. I've already found the derivative. Evaluating at -1 is really straightforward algebra. Just be careful. When I have a negative exponent, I want to move it to the denominator. So this is my first step, evaluating -1. I clean it up a little bit. What I did here, e to the -1 becomes e in the denominator, e to the -1 becomes e in the denominator, and e to the -2 becomes 1 over e squared. From here, I just am careful with my negatives and positives, and I clean it up to -10 over e, -10 e. Part B is a double chain rule. Part B is they give us h equals f of -2x. Therefore, the derivative would be the derivative of the outside, which is f prime, normal inside, times the derivative of the inside, which is f prime -2x, times the derivative of the inside, -2. So this is a double chain rule, not that involved. Once again, just as with everything else, from here, I then just evaluate it. And when I evaluate this at +1, I end up with f prime of f of -2, and blah, 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 like this. I don't even want to really go into my steps here because I think it's something you're fully capable of doing. You just need to be careful. Okay. Okay, number 9C is probably the most confusing one, mainly because it's dealing with arcsine, but it's exactly the same process. The first one talked about product rule, this talks about chain rule, or the quotient rule, whatever. So like these are just knocking off all the things you need to know about derivatives. In this case, it is both the product rule and the trig inverse rule. So we do the product rule here, derivative the first, normal second. I changed my notation from arcsine, sine -1. Plus derivative of the second, we can look this up, remember. Now this becomes 1 over the quantity of the square root of 1 minus this squared, right, times the derivative of this. So this 1/2 is the derivative of 1/2 x. So it's a derivative of the inside. All times normal first, and then we evaluate. So we take the derivative of the first, all this other stuff, then we evaluate at -1, and this we just need to be careful of. Sine inverse of -1/2 means what value of what angle gives me -1/2, and it becomes -pi/6 plus, and then this becomes, I clean this up to 1 over root 3/4, which becomes the square root of 3 over 2, because the square root of 4 is 2, and then I multiply by the reciprocal, and you get 2 over root 3, do not rationalize, and this becomes 1/2 times -2 here, and then I just clean this up a little bit, my 6's canceled, still negative, and that becomes that, okay? So two things here. The key is the inverse of sine derivative is right here, but we need to remember to use the chain rule till we multiply by 1/2. And then when we take the inverse of -1/2, we're talking about -pi/6 there because it has the graph. It looks like this. Okay, so there's my sine domain is -pi/2 to pi. Therefore, when we're talking about -1/2, we're talking about -pi/6.